Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be wrapping up our conversation on periodic trends by talking about a little bit of an odd topic, magnetic properties. So magnetic properties are one of those properties, kind of like electron affinity and ionization energy, that we really have to spend time looking at electronic configurations. So in order to figure out whether an element is magnetic or not, we actually really have to look at the valence electrons. So it turns out that, as we've seen, electrons all generate a slight magnetic field, most notably due to spin. And so if I have an electron with an unpaired spin, it's called paramagnetic. So a good example of this might be something like fluorine. I have a single unpaired spin, and so it will generate a slight magnetic field. This is going to be more emphasized when we have multiple parallel spins, thus paramagnetic. When all of your spins line up, you're going to have a much larger magnetic field. So while fluorine would be slightly paramagnetic, oxygen would be more so, and nitrogen even more. However, it is worth noting that this is all just looking at the atomic basis. However, you can do this same approach to look at molecular species. And this approach can also be very useful when looking at metal species. So if you go into the D block, you're going to notice, not too surprisingly, that iron is going to have a lot of unpaired electrons, and thus the reason it is such a magnetic element. However, if I have all of my spins paired up, then I'm going to generate no net magnetic field, and I won't interact with any magnetic fields. And this generates a diamagnetic element. So for example, let's go ahead and look at the fluoride ion. In fluoride, all of the spins are paired, and so it won't be affected by any magnetic fields because there's no unpaired spins to interact with said fields. So even though fluorine is magnetic, most of the time we don't think of fluorine as a magnetic element because it almost always exists in the ionic form where there's no unpaired electrons to do any set interactions. Not too surprisingly, all of our noble gases are going to be diamagnetic, and looking at other elements, all you need to do, draw the electronic configuration, and you should be able to figure out its magnetic properties. So I want to take a quick moment to help summarize all of the various periodic trends that we've been looking at so far this chapter. So the dominant features that we're going to be looking at is how much atoms want electrons. So for that, we can take a look at ionization energies. So ionization energies is how difficult it is to remove an electron from an element. This is going to be much more significant as we go up and over and up the periodic table. So when we get to elements like helium or fluorine, they're very bad at losing electrons. Not too surprisingly, non-metallic character tends to go along with these ionization energies, as it's very difficult to remove these electrons. If I have low ionization energies, this tends to correlate with metallic character, as the electrons will pass easily from one element to another. So low ionization energies, we tend to be fairly metallic in nature. Electron affinities tend to correlate with these ionization energies, but not perfectly, as we have a lot more nuance due to the influence of atomic and electronic radii, and they tend to maximize out here at about the third row, and we have a lot more fluctuation due to electronic configuration. Atomic radii tends to always get bigger as I have more electronic shells. So as I go down the periodic table, elements get larger radii. Also, when I have a lower Z effective or more less nuclei for each valence electron, we tend to also be larger elements. So kind of conversely to what you'd think, elements on the left side of the periodic table tend to be larger. And then we have other trends along the way, such as electron affinity, that are very vulnerable to electronic configurations, such as our magnetic properties. So when looking at these sorts of properties and keeping an eye on their influence for ionization energies, when in doubt, write out the valence electronic character, and you should get some idea of things like magnetic properties, ionization energies, and electron affinities. So this kind of brings us to the end of the chapter. Next chapter, we're going to go ahead and use these trends to help figure out how atoms tend to form together to make molecules. Until then, take care.